right? So that if you dropping in and out, or if you want to come back and rewatch it again later, you are, of course, more than welcome to. So let's go ahead and jump into our last room here. Here we go. That's the one. All right. So here we are, week 2 of IPC class, jumping into some basic properties of matter, basic ways that we can describe matter. Have you ever heard it referred as that before? Matter is just a fancy scientific way of saying stuff. So everything in the world, everything in the galaxy, everything in the universe is just all clumped together under one kind of general term of matter. So today we're going to be talking about the different kind of states of matter that we can observe and some different measurements that we can take about it. And then on Thursday, we'll get into some chemical and physical properties of matter, different ways that we can describe the matter that we are observing. Excuse me. Like I was saying earlier, I had some nasty allergy run-ins over the weekend, and I'm mostly recovered by now, but I still have just like a little bit left kind of clinging on there. All right. So states of matter and phase changes is what the first part of the notes we're going to be going over today. So you probably already are familiar with the states of matter without even realizing it. Things like solids and liquids and gases. And so you might be thinking, oh, solid, liquid, gas, that's like super basic. We learned about that in elementary school. What are we doing learning about that in IPC? Well, here we're going to go a little bit deeper than just kind of learning about the very basics. And we're going to talk about what exactly makes something a solid versus a liquid versus a gas. And so before we get into kind of the differences between those different states, we have to talk about sort of the basic principle that they are based on. And it's something called the kinetic molecular theory. So I know kinetic molecular theory is a big, scary, sciencey sounding term that sounds very confusing and terrifying. I promise it's not. It may sound complicated, but kinetic is just a fancy way, science way of saying motion or movement. And molecular is just like it sounds like, molecules, teeny tiny little particles, super, super tiny. And so the kinetic molecular theory, or KMT, as it's sometimes called, is just the idea that tiny, constantly moving particles, aka molecules, make up all matter. All stuff in the universe is made out of these tiny molecules, and they are constantly moving. So all molecules are constantly in some sort of motion. So one of the ways we measure how much motion that these particles are going through is temperature. So as the kinetic energy, so again, kinetic just means movement or motion. So as the kinetic energy of these particles increases, as the particles move faster and faster and more, the temperature goes up. So a hotter temperature means that you have more particle movement, and a lower temperature means that you have less particle movement. So that's all that this KMT is saying. Again, it sounds like a big, confusing, sciencey thing, but it really just means that all matter, all stuff in the universe is made out of these tiny molecules that are constantly moving. They're constantly in some sort of motion. And the hotter that they get, the more motion that they have. So that's going to be kind of the basis that we look at solids, liquids, and gases with. And we're going to relate them back to how much motion or how much energy that they have based on their particles. So I know that I just said that all matter is made up of these tiny particles that are constantly moving. And the first state of matter that I'm going to talk about is a solid. And so you might be thinking, but wait, Mr. Stanley, solids don't move. They stay very still. That's one of the things that they do best, right? So this water cup, my water bottle that I have, I can set it down on my table or I can hold it in my hand and it's not moving. It's not going anywhere. It's very solid. It's set in the shape that it's in. So that's true. We can't see any sort of movement going on with our eyes, but that doesn't mean that there isn't movement there down at the super tiny particle level. So solids have a very low KE or kinetic energy, so a low amount of energy. So the particles in a solid, they can move, but they can't like move around one another, right? They can sort of sit there and vibrate in place. So it's these super tiny particles making these super tiny movements. So we can't see it with our eyes. We can't see down to that sort of level. But that motion is happening. There's just not a lot of it. So solids have the lowest of the kinetic energy out of the three states that we're going to talk about today. So solids are also defined by the fact that they have what's called a definite shape and a definite volume, meaning that they have a set shape. Yeah, Gerson, exactly. Matter is everything that takes up space. So everything in the universe is built out of these tiny particles. So we just kind of clump everything together into a very general term of matter. So solids, the matter that we are talking about at the moment, they have a set shape and a set volume. It'll always be the same no matter what type of container that you put it in. So like my computer mouse right here, it's always going to be this kind of curvy shape, and it's always going to take up exactly this amount of space. So that's what volume is referring to, the amount of space that something takes up. So this will always take up the same amount of space because it is a solid. So whether or not I'm holding it in my hand, or if I put it down on the computer, or if I toss it over onto the floor behind me, it's still going to be solid. It's still going to be the same size and shape. Solids do not change their size and do not change their shape. It always is the same. Those particles are so stuck together, they can't move at all. They can only vibrate a little bit next to each other. So low energy in our solids, set shape and definite volume. Always going to be the same volume and shape. If we add in a little bit of energy to our system, make it so that our particles can move around each other a little bit more, we may end up with some liquid. So liquid has a higher kinetic energy than a solid. It has more movement in its particles. So they're not completely separate from each other. They're still kind of close together, but they can move around a lot more easily. They can change position and move and bend all over the place. So because of this, liquids do not have a definite shape, right? Whatever container that you pour the liquid into, that's the shape that it will take. So right now, the liquid that's in my water bottle is in sort of a round cone shape. If I pour it into my mouth, it will fill up the shape of my mouth. If I dump it onto the floor, it'll flatten out across the floor. So liquids do not have a set shape. they have an indefinite shape. They do not have a defined shape. It changes based on whatever container that they go into. What liquids do have, though, similar to solids, is a definite volume. There will always be a set amount of liquid. So, for example, if I pour out of my water bottle 1 cup of water into a measuring cup, and then I pour that cup of water into a pan, and then I pour that cup of water into a bowl, and then I pour that cup of water into a plugged up sink, it's still 1 cup of water. It has never changed the amount of water. It's still the same amount of water. It may have looked different depending on if it was in a cup versus a bowl versus a pot, but it still had the same volume. It was still the same amount of water. So like if we poured some liquid into our glass cylinder here, it's going to fill up along the bottom. The particles can move all over each other and fill up that shape on the bottom, but they're not going to get any bigger or smaller, take up more space or less space. It's still going to be a set amount of particles. It's just that they're filling up the container based on whatever shape of container that it is. So liquids, more energy, more movement than solids. Don't have a set shape. They can take whatever shape they need to, but they still have a set volume. A cup of water is a cup of water, no matter what type of container that you put it in. Oops. And then finally, the highest energy type of matter that we're going to talk about in this class are gases. So gases have the highest amount of kinetic energy. The particles in a gas are very far apart from each other and move very, very fast all around in the container. So there's a lot of energy, a lot of motion in a gas. Yeah, Larissa, go for it.
I've always wondered, like, you know how like they have like helium in a tank? Is it gathered as a liquid, or like how do they get it in the tank if it's gas?
So usually they'll have some sort of large source of helium, like a really, really, really big tank, and then they'll put pressure on the big tank and force the helium into like a smaller tank. So there's a certain amount of gas, like helium, that you can fit into a tank before it starts to pressurize to the point where it becomes a liquid. So if you put a gas at too much of a pressure, like you physically squeeze the particles close enough together, you can turn it into a liquid that way. But usually there is a lot of gas that you can fit in a certain area before that happens. Like kind of think about the air in your tires, right? We measure how much pressure there is in your tires to know if they need air in them or not. And so when they get too low, that means that there isn't as much gas in there as there used to be. And so you go to the tire pump at like 7-Eleven or whatever and pay the like $1, $1.50 or whatever it is. And it starts the machine, and then you hook it up to your tire and press the button, and it goes psh, 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 and it forces air into your tire. So because there's more air going into there, it increases the pressure. It's the same amount of space, but before the gas was kind of spread out. When you increase the pressure, you push the gas closer together, essentially. So they're able.
Okay.
The gas does get compressed down to a liquid, like I believe in propane tanks. If you've ever like switched out a tank at HEB, hey Guillermo, good to see you. If you pick it up, you can feel stuff sloshing around in there, right? That's because the propane inside of the tank has been pressurized enough to where it is a liquid. But when you open up the hose and connect it to your grill or whatever it is that you're hooking up your propane to, it comes out and it now is out of the pressure, so it's able to be a gas once again. Excuse me.
Okay, thank you.
It happens. Yeah, no worries. So that's a really good question and a really good point that brings to the next thing. So gases do not have a set shape or a set volume. So they can change shape and expand and contract their volume in order to fill up the entirety of a container, right? So if you pour some water into a cup, it's going to settle down and sit at the bottom unless you add more volume. If you put some gas into a cup and close it, the gas is bouncing all over the inside of the cup. So it takes up the entire space of the cup because there's no set volume for the gas. It just changes, it's constantly changing shape and volume in order to fit whatever container that you put it in. So a lot more movement, a lot more motion in gas particles than there are in solids and liquids. And because of that, they don't have any sort of set shape or volume. They can change or expand or contract based on whatever sort of container that they are placed in. So we have our solids, our lowest energy form of matter that have very set particles that gives them a set shape and size or volume. We have the liquids, the medium kind of energy level, more energy than the solids, but not as much as gas. Liquids have a little bit more motion, so they don't have a set shape, but they still take up a set amount of space, a set volume. Gases, highest energy particles, lots of moving around, lots of motion. And because of that, they don't have a definite shape or a definite volume. They will just take up whatever shape and volume of the container that they are placed in. All right, so that's sort of the particle basis behind our three different states of matter. Does anybody have any questions about our solids, liquids, or gases before we move on to the next part?
Right. I know I was a little late, but no questions.
All right, no worries. No worries. Thanks for being here. Okay. So with our solids, liquids, and gases, they're not going to stay that way forever. A lot of times we'll change from one type of state to another. And so we call that change a phase change. We change from one state or one phase, either being a solid, liquid, or gas, to one of the other ones. So a lot of these you've probably heard of before and are probably familiar with without even realizing it yet. So for the first change, let's think about when you have something that is a solid and you warm it up to the point where it turns into a liquid. What do you think that phase change is called?
Melting? Yeah, heat. I was gonna say heating.
No. Yeah, Stacy had it right with melting. That is exactly what it is. So melting is when you go from a solid to a liquid, right? You have your solid piece of ice and you put it on your kitchen counter and walk away for an hour. You come back and there's a little puddle on your counter. That solid ice has melted into liquid water. So whenever we heat up a solid to the point where it starts to change to a liquid, we call that melting. What about if we go back the other way? What if we have something that's liquid, but we cool it down and it turns into a solid?
Freezing?
Freezing. Bingo. Freezing is the opposite of melting. In freezing, you take something that is liquid and you cool it down past a certain point, and it turns into a solid. So you've essentially reduced the temperature, you reduce the amount of energy to the point where instead of those particles flowing around one another, they become locked together as a solid. So the point at which you go from liquid to solid, or from solid to liquid, is known as the melting point, or the freezing point, depending on which direction that you go. So for example, in water, the melting freezing point is 0 degrees Celsius. So if you take an ice cube and put it anywhere that's above 0 degrees Celsius, it'll start to melt and turn into a liquid. If you take some liquid water and put it somewhere that's below 0 degrees Celsius, it will freeze and turn into a solid. So the point at which we go from either solid to liquid or liquid to solid is called, if you're heating up, it's called the melting point. And if you're cooling down, it's called the freezing point. All right, what about our next phase change that you're probably familiar with? What about if you take some water and you get it really, really hot and it starts bubbling and giving off some gas? What do we call that change? What are you doing to the water?
Boiling it.
Boiling, exactly. And in science, because of course we can't just say boiling, we have to give it a fancy name. So in science, we call it vaporization. So vaporization is when we very quickly turn a liquid into a gas, specifically at the boiling point. So the boiling point is just whatever temperature a liquid has to hit before it starts to change into a gas. So when we're turning water into water vapor, when we put it on the stove and heat it up, we are vaporizing the water, turning it into a gas. So this is a very fast process. However, I also heard some people mention another process that can change liquid to gas, which is evaporation. So it's the same overall process. Liquid particles turn to gas particles, but instead of happening very fast, evaporation is a more slow and steady kind of process. So when you have like a big rainstorm, right? And it rains, and maybe the next morning you come outside and you see there's like a whole bunch of puddles along your street or along the sidewalk by your house or your apartment. And then the day warms up, you come back home after work, and now all those puddles are gone. They've all dried out. The liquid has seemed to disappear. Obviously, those puddles did not boil away, because if it ever got to the boiling point of water outside, we'd all be dead for sure. So that's not good. But the liquid still got changed to gas. And that's because evaporation is a natural process that happens over time, where liquid slowly changes to gas, even when you're not boiling it. So that water that was liquid turned into water vapor, but it took a while in order to do that. So vaporization is boiling liquid to turn it into gas, and evaporation is slowly changing from a liquid to a gas. Much like melting and freezing, we can also have an opposite reaction to this, which is called condensation. So condensation is going back the other way. We're taking some gas and cooling it down to the point where it becomes liquid. So this is the process that's responsible for things like clouds and rain. So there is a lot of water vapor up in our atmosphere. And when some of that water vapor cools down, the tiny water molecules start to kind of stick together. And that's what forms the big fluffy clouds that you see in the sky. It's essentially clumped up water molecules. Now, when you get a lot of those together and you cool them down far enough, those water molecules start to condense together and form little water drops that fall out of the sky as rain. So when we cool down the water vapor and the air enough and get enough of it together, it forms liquid drops that fall out of the sky, and we call that rain. And that's all thanks to condensation, turning a gas into a liquid. So those are kind of like the normal everyday ones that most of you guys have probably experienced at some point in your life already. There are two more, however, that are a little less common, a little more scientific, but they are still phase changes that can happen out in nature. So the first one is one of my personal favorite scientific words. It's called sublimation. Sublimation happens when we take something that is solid and it gets changed directly into a gas. So it's like we skip the liquid process entirely and go directly from a solid to a gas. Usually, this happens when we take something super cold and put it somewhere very hot. So an example,
like a fire extinguisher?
Sort of like a fire extinguisher, although, yeah, actually, yeah, that's true. You have the stuff packed in there that then gets kind of exploded out. Another example that you guys may have seen at some point, especially if you're at like a big party or a holiday gathering or something, is dry ice. So dry ice is frozen carbon dioxide. It's solid carbon dioxide. So in order to get carbon dioxide to freeze, you have to put it somewhere that's very, very cold. You then get these frozen blocks of carbon dioxide that when you expose them to the regular air temperature of like 70, 80 degrees, they heat up so fast because they're at like negative 100, 150 degrees, somewhere around there. So when they get exposed to that relatively high temperature, they heat up so fast that they skip changing into a liquid and instead go directly to being a gas. So that's why you see all this cool like smoke and fog stuff coming out when people like open the dry ice basket or like put some dry ice in some water or like a punch bowl, and it gives this cool like smoky foggy effect. That's because that is gas that is coming directly off of that block of dry ice. It's called dry because it never goes into a liquid stage and gets wet. It goes directly to being a gas. And so when that happens, when we heat up a solid so fast that it turns to a gas, we call it sublimation. There, as you might expect, is also a reverse process, which is called deposition. Deposition is like how you make dry ice in the first place. You take carbon dioxide gas and chill it down really, really quickly and somewhere really, really cold. And it goes from being a gas directly to being a solid. So sublimation, deposition, two sides of the same coin. One, you're going directly from a solid to a gas by heating up really quickly. Deposition, you're going from a gas to a solid by cooling down very quickly. So to bring it all together, we have this handy dandy little chart right here. So we have our solid where the particles are very tight, very close together, not moving a whole lot. If we heat up that solid enough, we can get it to melt and turn into a liquid. Particles are more flowing, more movement, they're not as stuck together. And we can heat up that liquid to where it's boiling or just let it change through evaporation and become a gas. That gas, with the super spread out particles moving very quickly, we can cool it down and condense it, turn it into a liquid. We could then cool that liquid down, freeze it, and it'll become a solid. And then finally, if we take that solid and heat it up extremely quickly, it will go through sublimation and become a gas. And if we take this gas and cool it down extremely quickly and turn it directly into a solid, it goes through deposition. So depending on how much heat or how much cool you apply to the system, you can change between one phase or another. So they're called phase changes, going from one to another based on the amount of heat and energy that is introduced. All right. Anybody have any questions so far about solids, liquids, gases, or the phase changes that they can go through?
No, sir.
Okay.
Yes, for me, Guillermo. Just to be sure, this chart that you're showing right now, so there's only 4 phases, basically, like the sublimation, deposition, and then the condensing, evaporating. Those are 4 different ones, or did those count as 2, just 2 or 3?
They're counted as 4.
I got you.
Different ones. So essentially, there's only 6 between these 3. There's only 6 changes that you could make, right?
Mhm.
You can go solid to liquid. You can go solid to gas. You can go liquid to solid. You could go liquid to gas. And you can
Or
go
gas
gas to solid
Okay.
and gas to liquid. So there's 6 different phase changes total.
Thank you.
No worries.
What was an example of the solid phase changing to gas?
So that would be
subliming, but
yeah, subliming or sublimation.
yeah.
And so that'd be like dry ice. If you've ever seen dry ice or gotten it from the store before, it comes in that like specialized packaging. And then when you open it up, there is this solid block of something that looks like regular ice, but there's all of this. It almost looks like steam or fog or mist that comes off of it. And it makes like these kind of waves of all this stuff coming up. And that's because the dry ice is extremely cold, like way colder than normal freezer ice would be. And so when it hits the air, even if the air isn't that hot around it, like 60, 70 degrees, the air is still way hotter than that block of dry ice. So instead of melting and turning into a liquid, the dry ice gets so hot that it starts immediately coming off as gas. So it skips over the liquid phase, and that solid starts to immediately turn into a gas.
Okay, thank you.
So it doesn't have to happen with dry ice. It can happen with most solid materials. As long as you get them hot enough, then they will start subliming and turning into a gas, skipping over that liquid phase entirely.
Hey, Mr. Stanley, isn't it supposed to be like really bad when you touch that with
Yes.
their skin?
Yeah, because that dry ice is so incredibly cold. Like I said, I think it's around like negative 100, 150 degrees Fahrenheit. That means they can instantly damage your skin if it touches it. It'll give it like almost instant frostbite. Let's see.
Ooh, that's bad.
Yeah, frozen at a temperature of negative 109 degrees Fahrenheit.
So when it's put inside your drink, or like, say like like you said, inside of like a punch or something that doesn't harm anything.
Right, because you're not touching it directly. The liquid that you put it in is absorbing all of that cold, essentially, which is why you put it in there.
Okay.
And all the gas that it's producing is coming out of the liquid and kind of like you'll see going over the sides of the punch bowl or whatever. So as long as you don't directly touch the dry ice with your skin, then it is fairly safe to use. So that's why you always see, if you ever see people like loading it or it comes in the special box, or if anybody ever touches it, they're using big like oven mitts essentially or gloves like that. That's to kind of help insulate your hands from the super freezing temperature of the dry ice.
Okay, makes sense.
Yeah, turns out our skin does not enjoy being placed in ultra cold places. It's not a fan of that. All right. Ooh, cool. Awesome questions. So I had a feeling that this part of it was not going to take super duper long. So, well, it is the end of our first set of notes for today. There is a second set that I have to go over that kind of directly brings in all of these ideas about states of matter and the motion of particles and changing between phases, all under one kind of area. And that is the concept of a heating curve. So a heating curve is also sometimes called a phase change diagram or a phase change curve or a heating diagram. A bunch of similar names, all talking about the same thing. It's essentially a diagram or a graph showing the temperature of a piece of matter, whatever it is that you're observing, as energy, usually in the form of heat, is added over time. So you can imagine it if you take a big block of something, stick a thermometer in it, put it on the stove, start heating it up, and take mark of what the temperature is every like 10 or 20 seconds, then you end up with something called a heating curve. So it's a way of seeing what the temperature in matter is doing as it gets warmer and warmer and goes through these phase changes. And so when you first hear about a heating curve, you may think, oh, it should just be like a straight line from it starts off as really cold, but then it gets warmer and warmer and warmer over time until it ends up as really hot. And it does get warmer over time, but it is not a straight line from being very cold to very hot. Instead, what scientists noticed when they were first studying heating curves is that they got something that looked like this. Don't worry about what all the labels and arrows mean. We're going to get to that in a second. But they've kept seeing this weird shape where it would start to heat up, and then the temperature would stay the same for a little while, and then it would heat up again, and then the temperature would stay the same for a while, and then it would heat up again. So instead of seeing this direct line from cold to hot, they got this kind of weird zigzag or stair step line. And so today I'm going to break down for you guys what each part of the heating curve means and why it is acting in the way that it is. So the first part of the heating curves that we're going to talk about are these areas where the temperature is going up. So you see over here on our y-axis, our up and down axis, we have the temperature in Celsius, because in science, we use Celsius to measure things. And on the x-axis, the horizontal axis, we have the amount of time that's gone by. So we stuck something on a stove at time 0 and are measuring the temperature for the next couple hundred minutes in this case. So what's happening in these areas where we're heating up? Well, it has to do with that kinetic energy that we were talking about earlier. Remember, with that kinetic molecular theory, I mentioned that all matter is just little particles that are moving. And the movement of those particles is its kinetic energy. So the faster that they're moving, the more kinetic energy that they have. Solids, low kinetic energy, not very much motion. Liquids, medium amount of kinetic energy, some particle motion. Gases, highest kinetic energy, lots of particle motion. Also remember, I mentioned that when you increase the temperature of something, you're increasing the motion and the kinetic energy. The hotter that something gets, the faster that the particles are moving. So the more particle motion that you have, the higher your temperature is going to be. So as your matter is sitting on the stove and heating up, the particles in it are moving faster and faster and faster as this temperature increases. So this increasing KE, this increasing energy, is happening at 3 spots on our heating curve. We have it first going up when it's a solid down here. It then turns into a liquid. It melts, turns into a liquid. So then our liquid starts to heat up right here. And then finally, at the very end, everything's turned into a gas. And so our gas starts to heat up over here on this kind of final tail section. So wherever this line is going up, that means that the temperature and the kinetic energy are going up. And that's happening when we're in one phase or one state of matter. So in this case, we're starting off with, this is a heating curve for water. So if we took like a big block of ice that was negative 20 degrees Celsius, plunked it on our stove, started heating it up and measuring it, we'd see that solid block of ice warm itself, get warmer and warmer until it reached this melting point right here, 0 degrees in the case of ice. Then once it turns into a liquid, that liquid that you put on the stove gets hotter and hotter and hotter and hotter until it starts boiling at 100 degrees Celsius. And then finally, once all that liquid is turned into a gas, the gas will start heating up as well. So whenever we're heating up, that's because we're in one state of matter, and that state of matter is just increasing in temperature and increasing in kinetic energy, increasing its particle movement. So down here, we're getting hotter as a solid. Over here, we're getting hotter as a liquid. And over here, we're getting hotter as a gas. So those parts are the parts that make the most sense, right? If you put something on the stove and turn on the heat, you're expecting it to go increase its temperature. You're expecting it to get hotter and the temperature to go up. But what about these weird sections right here and right here? They're not changing in temperature. They're starting and ending at the same temperature. So what's going on here? Why are things stopping going up in temperature? It has to do with something similar to kinetic energy, but a little bit different. And it's called potential energy, or PE. So before we had KE, now we have PE. The way that potential energy is different is that kinetic energy was all about how fast the particles are moving, how quickly they're moving around. one another. Potential energy is also dealing with particles, but it's not dealing with how fast they're moving. It's dealing with how close or how far apart are they. Potential energy is the space between the particles, how closely they are fused together. The closer you are, the less potential energy you have. The further apart you are, the more potential energy that you have. So when we're going through a phase change, when we're changing from one type of state to another, the potential energy goes up. More space between the particles means more potential energy. What that means is that if the potential energy is going up, our kinetic energy isn't being affected. And remember, kinetic energy is related to temperature. So whenever we're spreading out the particles, making them further apart, we're not affecting the temperature of the substance. So during these phase changes, the particles are not speeding up. They're not getting any faster. They're getting farther apart. Because they're not getting faster, the kinetic energy isn't changing, which means that the temperature is not changing. So those guys are staying the same. And that's why on those two parts on our heating curve, we had flat temperature with no change. So that's what's going on right here and right here. Down here, we're going from a solid to a liquid. So we are melting. And again, because we are changing phase, we're not increasing the kinetic energy and not increasing the temperature. So we're sticking at 0 degrees Celsius when we're melting from a solid to a liquid water. Then that liquid heats up for a while until it hits 100 degrees Celsius. And 100 degrees Celsius is when we start to boil or vaporize. So again, it's going to stay at 100 degrees Celsius while it's boiling. You can put a thermometer in as soon as it starts boiling, and you can put a thermometer in 30 minutes later if there's any water left, and it'll still be the same temperature. It should still be right around 100 degrees Celsius. Because we're not making the particles move faster, we're forcing them to be farther apart. We're turning it from water particles into gas particles. So while we're boiling or while we're melting, the temperature is not being affected. We're not getting any faster particles, we're just moving them apart. And that's why we have these flat areas on our heating curve. The temperature is not going up because our phase is changing. We're going from a solid to a liquid, or from a liquid to a gas. So when our temperature is going up, that means that we are staying in one phase and the temperature of it is just increasing. We're heating it up. When the temperature is flat and not changing, that means that we're changing from one phase to another. We're transitioning between a solid to a liquid or a liquid to a gas. And when that's happening, we are not changing the temperature. So if we put it all together and sort of think about the path of this ice block from being a big solid piece of ice to water vapor floating in the air, we get a story that looks something like this. We start off with a very, very cold piece of ice. We put it on our stove and start warming it up. At first, the ice block just starts to warm up. It's not melting, there's no water, liquid water coming off, but the ice itself is getting warmer and warmer. Until finally, bam, it hits its melting point, which for water is 0 degrees. So at 0 degrees, a solid block of ice will start melting. while the ice is melting, the temperature is still staying the same. The temperature is staying right around 0 degrees Celsius. So we start as a solid, and we're melting and melting and melting at 0 degrees until it all becomes liquid water. Then once that solid is all gone and we're all liquid now the liquid starts to heat up. It starts to absorb that heat. Its particles are moving faster, and they're moving faster. The kinetic energy is going up. The temperature is going up, and we're heating up until, bam, we hit water's boiling point, which is 100 degrees Celsius. Now our water is boiling. We're starting to give off lots of gas. But while that water is boiling, the temperature is staying the same. While the boiling is going on, we're going to be right around 100 degrees Celsius. We're taking all that energy from the stove and using it to break apart the water molecules and turn them into gas. So we're boiling and boiling and boiling, staying at the same temperature until finally all of the water has boiled away. It's all been converted into gas molecules, and now the gas is able to start heating up and getting hotter and hotter itself. So when we go on this journey with water, or really any type of molecule, any type of matter, they're always going to follow the same general plan. Start as a solid, heat up until you hit the melting point, stay the same temperature as you melt and turn into a liquid, start heating up as a liquid until you hit the boiling point, stay as the same temperature while you're boiling into a gas, and then finally get all turned into gas and start heating up again once all the liquid water or liquid has boiled or vaporized away. So that's why you get this stair-step kind of function on these heating curves. It's because sometimes the temperature is going up as we're staying in one phase, and sometimes the temperature is staying the same as we're changing phase. All right, and again, in the case of water, our melting point down here is 0, and our boiling point up here is 100 degrees Celsius, which is about 32 and 212 degrees Fahrenheit. But again, in science, we like to use Celsius because of this reason. It gives us nice round numbers for water, like 0 and 100. All right. So I know that was a whole lot about energies and states and changes, diagrams that I just threw at you guys. Does anybody have any questions about our heating curve here? Anything about the heating curve that you want me to go back and explain a little bit more or clarify a little bit more?
I have a question. On the questions, is it ever going to ask like the exact temperature for each matter? Like do we have to guess or?
Not really. The only one that you really have to know for sure is just the melting and boiling point of water.
Melting.
So if you know that water melts at 0 degrees and boils at 100 degrees, that's really the only thing that you need to know in terms of specific temperatures. Obviously, other matter will have other melting and boiling points, but we don't really need to worry about trying to remember those for this class, at least.
Okay, I have another weird question. So
Yeah.
like say like a solid, like does this go for like any solids like wood?
Theoretically, yes. Wood might be a little bit different because wood is made up of a whole bunch of particles. Like there are tons of different structures and compounds in wood that might not really melt that well. But if you think about things that are sort of less complicated, so like plastic or metals or like natural gases and natural liquids, those things will have very similar types of heating curves.
Okay, thank you.
So like the metal in my water bottle, for example, you could get this to melt and get it to boil if you're able to get it hot enough. And it would go through the same general phases, the same general kind of outline as the heating curve for water. All right, great questions. Any other questions or anything about the heating curve that you still want some explanation on?
I missed some of the, like, because I was writing down, like, for notes. I remember in the first class you said that you're recording these, right? So I'll be able to go back.
Yep, every class will be recorded and posted on the Google Classroom shortly after class is over. And then the notes are also available if you ever want to go back and just look at those on your own time as well. Those are always available to you guys. Alrighty, so that was our heating curve. So your homework for today and tomorrow's assignments are fairly straightforward and pretty closely go along with the stuff that we were just talking about here. So for today's assignment, for Tuesday's homework, it's split up into a couple of different sections. The first part has a little reminder about solids, liquids, and gases. It talks about plasma too, but we're not really going to cover plasma in this class, so don't worry about that too much. And then it gives you these three diagrams, the left, the middle, and the right diagram. And so for the first part, I just want you to tell me which of these diagrams most likely represents a liquid, which one most represents a solid, and which one most represents a gas. So that's sort of the first three questions right here. You then have a little segment that kind of summarizes the major phase changes that we talked about. And then the second part, I have this ice, water, and gas kind of triangle, very similar to the one that we looked at the end of the notes today. And we have, excuse me, and we have these labeled arrows right here. So arrow 1 is going from gas to solid. Arrow 3 is going from solid to liquid. Arrow 4 is going from liquid to solid. So forth. Thank you, Alexandra. And all you have to do is tell me which phase change corresponds with which arrow. So for example, is arrow 1 melting, freezing, condensing, vaporizing, sublimating, all that good stuff. So you'll match each one of these arrows 1 through 6 with one of the phase changes that we talked about in class today. So arrow labeling and diagram labeling for today's homework. And then tomorrow's homework, Wednesday's daily assignment that you can do for attendance, should be posted in just a couple hours here at the very beginning of Wednesday. It has a heating curve, very similar to the one that we just looked at. This is a heating curve for water. So you have an ice cube, you place it in a beaker and begin to heat it up and then keep track of the temperature. So the heating curve looks a little bit different from the one that we looked at on the slides, but it's the exact same basic shape, right? We have this area where we're going up and then we're flat for a little bit and then we go up again and then we're flat for a bit and then we go up again. And each kind of point on the curve is labeled. And so for tomorrow's homework, it's just a series of questions about what is going on sort of between each one of these labels. So number one, you have an ice cube, and you just have to say what's going on between A and B, and then what's happening between B and C. It mentions about measuring the temperature. So again, this is water. So the temperatures that you see here should match up with the temperatures from the example that we were looking at a second ago. So it says if you were to measure the temperature between B and C, what would you read on your thermometer? And then what's going on between C and D, D and E? It asks for another temperature check between D and E. And then finally, what's happening between E and F. So you're basically just sort of walking me through what's happening at each stage of this heating curve. Again, slightly different design, but has all the exact same parts as the one that we were just looking at. All right. And then when we come back together on Thursday, we'll talk about different sorts of chemical and physical properties that different types of matter can have. All right. So does anybody have any final questions about any of the notes from today, the states of matter, phase changes, the heating curves, or any of the different parts of the assignments for today and tomorrow?
No, sir.
No, sir.
Alrighty.
No.
Let's do this.